Okay, so this is the first of 3 talks about what to do that is even better than Gaia. It's hard to imagine anything better, but in fact, we're going to hear about 3 different possible missions that will go beyond Gaia in many different ways. So the first one is the JASMINE mission, Japanese mission, and Kawata-san will give the talk on that. Thank you.
Yeah, thank you. Thank you. Yes, first of all, thank you very much for the great organizers giving me this opportunity to introduce our JASMINE mission from Far East. And this is Japan Astrometry satellite mission for near-infrared exploration. So we hope that we can continue the success of the Gaia and making a good impact for the wide range of science, including exoplanet science. So I'm Daisuke Kawata. I'm a JASMINE project scientist, and I should make a big credit to the Naoto Goda. Goda-san who is the founder and godfather of the JASMINE project, and he's an NLJ, and he's a principal investigator of this mission. And also Hajime Kawahara, who is a exoplanet science lead, who helped me to tweak my usual JASMINE mission slides to exoplanet on, because I'm originally, I'm still a galactic scientist, like what Melissa talked in this week. And I learned quite a lot in this week, and I understand that why people are so excited about exoplanet, and it's very sexy, in fact. So we are to also, I will tell you that JASMINE also have some great weight in exoplanet science too. So I hope we can please you all as well. And also, interestingly, I found quite a common thing in 3 of us. And all of us, including Goda-san, we are started our career as a theorist, and in fact, the pure theorist. He was a cosmologist, and Hajime was doing a cluster of galaxies, and he started his career, but now he's expert in exoplanet. And I'm also theorist, and mainly working for the galaxy formation evolution or Milky Way formation evolution. But now we are dedicating to the space missions. So yeah, it's interesting now how our career moved, and I think being open-minded and excited is quite good. And luckily, this JASMINE mission is not a theoretical idea, but this is a real mission. And I can talk about now that this is coming. And yes, it is having a very good momentum, and hopefully it will be adopted in next year. So, but I first would like to respectfully talk about some history in the Japanese astrometry mission. It started around the 2000 by Naoto Goda, and here it's theorist is ambitious, I think, and I think this worked very well. But still, it's very nice to see that. And he had the idea in 2009. We have 3 Japanese astrometry mission launching within 10 years, starting from nano JASMINE, and also small JASMINE, which is 30-centimeter telescope, and going to the large JASMINE 80-centimeter telescope, mapping a whole bulge region and doing a near-infrared astrometry. And in fact, it's a nano JASMINE as built, and it's like a size of this huge box, and it is in the clean room in the Tokyo. And but unfortunately, in some uncontrollable accident happened, and not accident, it's a incident happened, and it couldn't launch. And if you're interested in, I can talk about it, but not in the recorded talk. So unfortunately it didn't, but it's great to have this kind of idea and showing around. And then now Japan has a nice launcher called Epsilon. It's small rocket, and it's quite economical. So Japanese people, Japanese government and Japanese Space Agency want to launch as often as possible. And they found that this small JASMINE idea is just in the size of this small rocket. So it is sort of dragged, and now we are selected by the ISAS and JAXA, thankfully. And Okay, we want to have the big one as well, but Koda-san is also close to retire, and this is great to have just one JASMINE at least. So now we no longer call this as a small JASMINE, but now we call JASMINE. So this, whenever I said JASMINE in the talk, this is basically this small JASMINE concept, which is Koda-san had almost 20 years ago. And we hope that the next speaker, David Hobbs, will talk about the Gaia near infrared, the success of the Gaia in the near infrared. So we can be a pioneer for the near infrared astrometry and much smaller scale, but we can make it being a sort of stepping stone to the bigger mission and also build expertise in Japan. And we can hopefully join that to the Gaia near in the 2040s, hopefully. Okay, so the JASMINE is now selected by the JAXA and ISAS as a M-Class mission we call, and which is a near infrared astrometry and the time series photometry mission. And as I said, if this is the Epsilon rocket, and Japan has an ambition to launch this kind of M missions every 2 years. So this is an interesting opportunity for our international friends. If you have some interesting idea of this small satellite, talk to the Japanese colleague. I think this is a quite great opportunity, which is not very well known internationally. So you can build nice small satellite missions with your Japanese colleague, because we just want to launch this fantastic rocket. So, okay, JASMINE is 36 centimeter diameter mirror, just a single telescope, a single focal plane. It's quite simple, but we are doing that in the focusing on the near infrared regime. It's 1 micron to 1.6 micron, which is basically J band, but we call this is the HW band sneakily, and because it's slightly sort of touched H band as well, and H band is in fact is quite nice. But this is basically J-band mission. Okay, sorry about Japanese one, and you don't have to read it or understand this. But one thing I really wanted to highlight is this is the Japanese space science program roadmap in the cabinet office in Japan. This is the most recent one, and this is the year. You can see that this number at least, and this is 2028. And this is JASMINE. You can see this. This is small JASMINE, and there is this in the roadmap. It's already in the JASMINE there, and it's in the cabinet office. Our launch is 2028, and we are working toward it. And we are having a good team now, making a good effort to launch JASMINE in 2028. Okay, so we have now Japanese consortium in the Japanese team, and also the international interest there. And we are talking to our international friends, and hope they are now start helping us as well. So going to science, JASMINE is sort of a dual aim science, and that we have two main science goals. One is the galactic center archaeology. So we will look at the galactic center for 3 years to get the near infrared astrometry to reveal that the Milky Way central core structure and its formation history. And also that hopefully tell us about how the galactic Milky Way structure, like a bar, when they form, and that probably quite important. I think Melissa talked about radial migration, and sun also must have been influenced by the radial migration as well. And the bar is quite key things. So it's getting the age of the bar is quite important, and it's important for the history of how the sun stars with the exoplanet move around within the Milky Way. And we target the galactic center, which is untouched territory in Gaia. Even Gaia couldn't see that. So that's sort of niche there. So that's where we're going. But it's, in that same time, late 2020s, we have a lot of nice ground-based multi-object spectrograph, near-infrared multi-object spectrograph is ready to map all the stars. So having a proper motion with the spectrograph data is great idea. So I think we are going for it. And another one is Exoplanet. We are doing a transit, looking at transit for the M-dwarf. and trying to discover that Earth-like habitable planet around the M-dwarf. And it will be a very good timing as well. Again, hopefully JWST will stay for a long time. And also Ariel in the ESA mission, a spectroscopy mission is also coming along in the late 2020s as well. So we try to feed them to the nice target list discovered by our transit survey. So although of course I know that this is the Exoplanet mission, but my heart is also on the galactic astronomy. So please forgive me talk about a bit about galactic a context of the JASMINE mission as well. So we are going to look at the galactic center, which is not possible to look at the Gaia because of the strong dust extinction. But then in infrared, you can see through the dust and you can see the movement of stars or distance to the stars by parallax. Looking at the same region 3 years. So we are targeting this region within the 200 parsec from the Sagittarius A star. And so, but it's a small telescope. So that is what we can do. And this is the galactic center region. It's like a 1.4 degrees square, 1.4 degree field, and with a sort of a bit of extension. So that's what we are trying to map out. And we're hoping to get like the J band or HW band up to 14.5 magnitude. So we can get nice astrometry of the 100,000 stars. And so that, but the accuracy is, we try to get that the whole bright stars, we can get the 25 microarcsecond accuracy in the parallax, and but 14.5 we probably degrade to the 0.1 milliarcsecond. But still you can get 5 kilometer second accuracy, so it's quite great to understand the structures in the galactic center. And but at the same time, we are doing to achieve this astrometry, we are doing time series photometry. So you get the time series photometry for free. So hopefully that is also useful for doing micro lensing or variable stars and etc. as well. And yes, we are trying to focus on the galactic center. And one thing we are setting this mission is that we can look at the nuclear stellar disk. And why nuclear stellar disk is interesting? Because so we know now, have some idea of how galaxy forms in a high redshift galaxy. Now we can see in the JWST that there's a lot of small merger is going on. But then the lambda CDM tells us less merger happened, and then nicely gas created to the center of the dark matter and make a very nice thin disk or thick disk. And then in the Milky Way, we have a bar like that. So some point this bar have to form. And as I said, the bar formation is quite important. And maybe sun maybe moved from the inside of the galaxies and came to the outside, because sun is in fact more metal rich than the stars around us. That's also Gaia DRC clearly show that. So that sun must migrated as well, and bar probably the key things. And so we want to get when the bar formed. And the key observation, we can tell that when the bar form is, we think the nuclear stellar disk, because it's when the bar form, the gas lose angular momentum and plunge into the center, and there's a stable orbit called X2 orbit in the galactic center. And after the bar formation, and you can make a star formation, very stable star formation. And it's very difficult to break. So you should have a nuclear stellar disk once bar form. So if you know the formation time of the nuclear stellar disk, that should be the same time as the bar formation epoch. So that's what we are going for. And it'd be nice to answer that. The bar form first, and after that, sun form, or sun form first, and then bar formed, and then maybe sun is moved by the bar, radial migration due to the bar. So that's quite an interesting thing we want to address. And yes, it's nice. Radial migration is quite important, and even new scientists can think about write very nice articles and why that is important, but I will skip that. And how to get the age of the nuclear stellar disk, we use a MIRA, so the variable stars. And so it's whatever variable one is, you can get free from JASMINE data. So that's one of the demonstration. Because MIRA is very bright, and also there's a period age relation there. So if you find the MIRA with a period, and then you can get age. So you can do the period distribution, and then you can tell that, yes, there's a lot of younger or longer period MIRA there from, let's say, 250 days. And then that is probably the age of the MIRA, age of the nuclear stellar disk when they form. And the proper motion is very important because the nuclear stellar disk is rotating. So you can get rid of this contamination of the other bulge stars, which is not rotating. So you can pick up only stars within the nuclear stellar disk, and you can make an age distribution for that. And but it's MIRA is a quite long time period variable, so 3 years may not be enough. So we have a prime telescope, Japanese people led by Osaka universities already start making some effort in South Africa. This is a near infrared photometry mission, just looking at pouch region all the time in many, many years. So that's a great telescope. We can identify the MIRA before JASMINE happened. So, and one more thing, I'm also excited about. This is a similar idea to how you also we discussed how to do the astrometry in the Hawaiian exoplanet, but we can also do the same technique and find the black hole as well. And it's quite interesting to do that in the galactic center because so far we know that there's a lot of black hole mass whose mass is less than 100 solar mass thanks to the gravitational wave telescopes. And also, thanks to the huge effort, 20 years of effort in looking at adaptive optics data in the Galactic Center by US and Europe. And of course, we went to the Nobel Prize. And then we know that there's a black hole in the Galactic Center, but whose mass is like 10 to the 6 solar mass. And the smaller galaxy also had supermassive black hole, like 10 to the 5 solar mass. But we don't have the stars in this, black hole in this mass regime, which called the intermediate mass black hole, which is quite puzzling. They should be there, but nobody found it. But it's probably they may be hidden in the galactic center, and because the galactic center is the exotic place, and yeah, it's maybe some runaway collapse may happen near the supermassive black hole, or remnant of the ancient merger from dwarf galaxies may bring the small black hole or intermediate mass black hole, and they still may not have merged yet. And so the free floating 10 to the 4 solar mass black hole may be there. And as we discussed in this week, and if you see the stars around something in the black, and then we can identify the mass of that. And we are expecting that we will get some 30 non-interacting black hole binary from this mission. So we hope that one of them could be a quite high mass. And another method is microlensing. It's quite also a galactic center microlensing. We always have to think about that. And we are expecting 10 micro lensing event to happen in the JASMINE field if we map for 3 years. But it's not usually microlensing is a photometric, but recently a huge effort by the Hubble Space Telescope team and the microlensing team have found that in a 7 solar mass black hole using astrometric microlensing. So you can see that not only the brightness change the background stars by the lens, but you see the centroid change due to the position of the lens. So you can, so then you can degenerate, you can resolve the degeneracy of the speed of the lens, and then you can get a very accurate mass of the lens. And Toki and Takada estimated that if there is a black hole in the galactic center, like 7.5 kiloparsec away from us, and then the signal, 1,000 solar mass, then signal should be like last 700 days, and also the huge asymmetric movement of this microlensing event, which is 8.2 milliarc seconds. So it's very easy for JASMINE to detect that. And we can, but these events are very, very rare, and you have to look at the faint stars as well. So we are hoping that at the same time, the Subaru will have adaptive optics, grand layer adaptive optics instruments, so we can map the galactic center region same time as JASMINE. So you can use the JASMINE reference frame and try to do the same thing with Subaru Ultimate as well. Okay, enough is enough, and it should go back to the exoplanet. And okay, but this is the transit, and it's just 5 more minutes. Okay, and so this is a 3 years mission, but we are not going to L2, but we are in a sun synchronized orbit around the Earth. So we can only see the galactic center in autumn and the spring. And in the summer and the winter, we will try to look at the M-dwarf transit, and led by the team by the Kawata-san. And in fact, there's a lot of M-dwarf we can see in the summer and the winter. And it's an interesting thing in the JASMINE is it's a near infrared mission. So we have more light from M-dwarf in this 1.0 and 1.6 microsecond regime. So our strategy for doing this transit survey is basically we try to find that Earth-like planet in the habitable zone, and it's going to be like a 0.2 and 0.3% transit depth. But we have now the good simulation, and Hirano-san did a quite nice simulation, and they demonstrated that we can achieve this. And we are, I think the niche of this JASMINE M-dwarf survey is, TRAPPIST-1 and Spitzer combination of that. It can really find that nice habitable zone planet. And TESS is now doing a quite fantastic job. And also we had that in a flagship and the Roman here, they're targeting like a sun-like stars around exoplanet, sun-like stars. But the JASMINE is basically filling a gap between TESS and the ground base, and we are trying to fill this gap as well. And the strategy is very similar to what the Spitzer was doing, so that we can get this kind of ground-based detection of transit in probably the much shorter orbit, and then we can follow up in space and try to find that in a habitable zone planets. Okay. And I think it's another interesting thing. It's not only picking up this kind of the targeted M-dwarf, but because the JASMINE has a 0.5 degree field of view and very small pixel as well, so we can target a star cluster. And in fact, this is M39, and you can see a lot of stars. And this figure is showing that in a galactic longitude and latitude, and these circles are basically showing that how many Earth-like transit we can detect with a JASMINE, or how many Neptune-sized transit we can detect. And so in fact, for example, this NGC 6475, we can detect like 1,000 of the Earth-sized exoplanet, or 1,000 of the Neptune-sized planet. So I think it will be quite exciting one, and hopefully we can get some astrometry information as well. And of course, astrometric survey we can do that. It's Gaia will do it, and but that we can get this very cold L-type dwarf and etc. So that's going to be a quite nice target for JASMINE. And yes, ultra cruise dwarf, it's very cool. Apparently, the Jackie really excites us a lot as well. So we can target those stars and get the astrometry of these stars. And also we can follow up radio velocity and direct imaging a long period planet combined with the Gaia astrometry. We can make 20 years of baseline or even more, and then we can detect these kind of things. And also the astrometric microlensing is, again, it's quite interesting one. Of course, galactic center one give you a nice astrometry information as well. Do we have 1 more minute or 1 minute? Okay. So this is the payload, but we have 4 detectors, but I just want to say that this detector, infrared detector, will be a Japanese detector, and we are quite excited by that. And we are also thinking of putting a flat in the space. That would be quite exciting. And we now have a quite big effort for doing a mock observations. And in fact, like 3 years of the JASMINE observation is like this, and getting astrometry from this is quite challenging. And we have a very good team in Japan, and also have people in Heidelberg is helping for that. And so we hope that we can build and be prepared very well for this JASMINE mission. And I think that the iterate, and it just means a great timing because of the overlap with the JWST, Roman, Ariel, and hopefully bridge the Gaia to Gaiania. And so we think we really should launch in 2028, and we are pushing for it. And this is my summary. And yes, we are quite a young team and small team, and any help is very welcome. So any in-kind contribution is very welcome. So please join to JASMINE. Okay.
Maybe one question here. I guess I'll ask one question. You're focusing on the galactic center region, and you'll do the absolute astrometry by linking in Gaia stars in that region.
Yes, so that's quite important to use all the epoch astrometry from Gaia and extrapolate it. So we hope that we can work very closely with people in Europe.
Eric?
Eric Ramacek, NASA JPL. I was going to ask you, do you anticipate overlap between your galactic center survey and the Roman microlensing bulge survey? And are there synergies there? Maybe the ability to measure parallaxes for microlensing events? How much overlap might there be?
It's there. As long as I know, they don't have any overlap. It's a bit of a shift. I think they're going to Bodies window, but Galactic Center is not very nice. But we are talking about that. They have a K-band now, so maybe there's open time. And I think Japan is also joining the Roman, so hopefully we can also do some survey in the Galactic Center and overlap with JASMINE. Would be fantastic. Yeah, thank you for asking.
Okay, well, thank you very much.
Yeah, thank you.